Hello! In this unit we are going to study the real numbers, the set of R. The objectives that we pursue include defining real numbers and examining the operations within R and the properties that these operations have in the realm of real numbers. The requirement is to have a solid understanding of rational numbers and their operations, as we have seen in our previous lessons. As we've seen in previous units of this course, the origin of numbers always comes from a natural problem. In this case, we can illustrate or motivate the origin of real numbers with a simple and natural problem. Consider a square with a 1 alongside it. In other words, it means that all sides are of equal length, which is 1. How much is the diagonal? Well, to solve this problem, we can use the known Pythagorean theorem, which states that this diagonal is essentially the hypotenuse of a right triangle with sides of length 1 and 1. Therefore, what will happen is that the sum of the squared legs will be the squared diagonal, the squared hypotenuse. Therefore, we encounter that our problem is reduced to finding a number d whose square is equal to 2. That is, we want to solve the equation x squared equals 2. Is it possible to solve this equation? Is there a rational number whose value satisfies that its square root equals 2? The answer is no. The answer is that if we look for a solution in the set of rational numbers, we will not find such a number. Therefore, we define a new number which is the square root of 2, and initially it is not part of the set of rational numbers. Thus, we are expanding the set of rational numbers to new horizons. From this problem, what we can observe is that there's a need to introduce additional numbers. In this case, we will provide a slightly unconventional definition of what real numbers would be. To do this, we will utilize the decimal numbers that we all know. It's understood that any rational number can be represented as a decimal number. In particular, a rational number, upon division, can result in an exact decimal number. That means that the decimal number ends after a certain point, like in the example we have here, 2.5, or that it can result in a recurring decimal, such as 5/3, which when we calculate it results in 1.6666. The indefinite repetition of the 6 represents the period in the presentation, which is the real reason why these numbers are referred to as periodic numbers. However, there are other types of decimal numbers as well. Any decimal expression like this, but that it is infinite, it doesn't end, and that it does not have a period, it doesn't have a repeating pattern, gives us a new decimal number. Well, we are going to call these decimal numbers d, and those that are not exact or periodic, those that are infinite and do not repeat or don't have any repeating pattern, are called irrational numbers. They are going to be numbers that are not rational, and therefore they are called irrational. They are not called irrational because they do not think or act irrationally, but because they are not rational. They are usually represented by the I of irrational. What is our definition of the real numbers? Well, for now and for practical interest, for us, the real numbers are exactly the decimal numbers. In other words, the rational numbers and the irrational numbers together. All their decimals are what make up the real numbers. Then, given a real number, it can be either rational or irrational. The operations introduced in R are the ones that we are all used to using, and they are actually inherited from Q. Starting with the natural numbers, these operations are inherited and extended to the whole numbers. Subsequently, they are introduced to rational numbers, and from rational numbers, they are further extended to real numbers. These operations are addition and multiplication, as we have reviewed in previous sections of this topic. The real numbers also have some significant properties for their operations, including associativity, commutativity, the existence of neutral elements, and the existence of the symmetric element for both addition and multiplication. And of course, the distributive property of the product with respect to addition. As we already said previously, when we talked about Q, these properties in a numeric set give the set a name, which is field. The rational numbers form a field, and the real numbers also constitute a field, as they exhibit the same properties. Well, so far what have we covered in this unit? We talked about the definition of real and irrational numbers, reviewed the operations, and saw the fundamental properties of these operations that endow R with the structure of a field. These are some questions for reflection. Would you be able to justify why square root 2 is not a rational number? And another question, do you think that every quadratic equation has a solution? How many solutions does the equation x squared plus x plus 1 is equal to 0 have? We have been adding numbers from problems with equations. Equations that did not have a solution in the set of numbers we used. We will realize that there are still equations that do not have a solution, and for that we will have to add new numbers, but we will see that in other sessions. Thank you.